Welcome back, everybody. Hopefully you have all had a good lunch, and I will give you a very inspiring talk about the challenges that we face in HPC as a system builder. So I'll talk about hardware first, and then I will switch to software very quickly, because that is, at the end, all that matters. So there's a lot that is going to change in the coming year. We are probably facing more and more competition. We have new CPUs. We have the comeback of AMD. We have ARM. We have IBM with Power. And we will get new Intel chips. So there's a lot of choices. And we also see a shift now, because of all those hardware choices, that we can make very smart choices with regard to the hardware. And we don't necessarily have to tune our software, but we can also tune the hardware with all the tuning knobs that we have for the workload. So this is a quote from the Vice President of Microsoft Cloud Solutions, who says, well, you don't have to tune for software anymore, but hardware tuning is actually more important. And if you want to have the best bang for the buck, then you have to tune both. For us, we still have the most two important laws in our industry. We have Moore's law on the left, which says that we are hitting all kinds of barriers with regard to the power consumption, the frequency, and the per core performance. We still see that the Moore's law in terms of the number of transistors per chip is true. So we are still getting more transistors every 18 months. But at the same time, if we look at efficiency, and that is where Amdahl's law comes in, then we can see if we want to use those cores efficiently, that we really have to parallelize very well. And you see here various efficiency numbers, or percentages, I should say. We have 50, 66, and 75%. And you can then really see if you want to get a 50% efficiency, which means 32x on 64 cores, that then, if you look it up here, then you have to be way above 99% parallel. So obviously, you have to work really hard in order to unlock all that efficiency. So you can say, if we combine both laws, then we have too many cooks in the kitchen, because Moore's law says we are getting more cores, but Amdahl says you cannot use them all efficiently. So what does that then imply for us? At the same time, for systems, we are seeing a trend. In the old days, where we had the big iron systems from IBM, HP, Silicon Graphics, and Sun, we had, you could say, a big bus here, and everybody was attached to that bus. We had CPUs, we had a network card, we had the memory controller, and we had the memory. And everybody, or every CPU, had the same view of the memory. Then we entered the multi-core era in 2005, where we had the first consolidation going on, you can say, where we had all of a sudden multiple processing units on the same chip, but again, more or less the same view of the memory and the network card. Then, later on, with the introduction of the Intel Sandy Bridge, the Hilgeman, we had the integrated memory controller, and all of a sudden, the system did not have a uniform memory layout. Not all cores had the same view of the memory, because this memory here is local to these cores, while the memory on the other chip is local to these cores, but not to the other. But still, when connected to the outside world, you can say a uniform view of the world. Then with Sandy Bridge, we all of a sudden got the PCIe controller on the chip. So you can then see that we are getting one extra imbalance, not only the memory, but also the network card, because this is closer to here than it is for the other cores. And obviously, we are now getting, with the Intel OmniPath, we are getting an integrated network adapter on the chip, where you can have a balanced system or an imbalanced system if you combine a non-OmniPath version with an OmniPath version of the chip on the same motherboard. And for the future, it will even become more integrated, where we will be getting systems on a chip. So we will get a CPU with a combined DSP or FPGA device. So you can see it is all becoming very much integrated. Hardware is more or less becoming a black box with a big amount of capabilities. So what does that imply for us as system builders, you can say? People are expecting for us that new systems have better performance and for a similar or lower price, and the power consumption, the real estate, and the reliability numbers need to be at least equal or better than the predecessor. So you can say, how do we do that for new systems? Well, we don't have a single answer, but we can turn architectural knobs with regard to performance. So we can tune the frequency, we can increase the number of cores per socket, or we can increase the number of sockets, or we can increase the capabilities of each individual core on that system. So this is all hardware, and then we multiply that by our MDAL number, you can say, or our efficiency. See? So this is determined by the software, the rest is hardware determined. So what if we turn the knobs? And we start with knob 1. Well, we know that frequency is not very likely to change because we are more or less around the 2-point-something gigahertz. It's not very likely to change because of the power consumption and the leakage. Number 2, that is our Moore's law, or the number of cores per chip. It's still increasing, right? We are now on 40 nanometer. We will be getting a 28-core chip from Intel very soon. AMD will have a 32-core chip even, so lots of cores. So that is still increasing. You can say that we can increase the number of sockets on the board, but however, if we do that, then we will suffer with regard to power consumption, with real estate and cooling and networking. So that is not the answer. Then you can say, look at the capabilities per core. Luckily, we are currently seeing an increase of the number of instructions per cycle. So cores are becoming more capable, not only in what they can retire in a cycle, but also what kind of instructions they can retire. Because we now have the FMA instruction, we have AVX, we have other special instructions, or we can use an accelerator as well. That is also what I call a special instruction. However, number 4 is challenging for the user or the developer because our computer program needs to be adopted in order to make use of those instructions. So what is Intel is telling us? You have seen this all before multiple times, so I will go through it quickly. They have that tick-tock, where you can say a tock is a change in microarchitecture on the same process technology, and then a tick is a change in the process technology giving a smaller transistor size, so we can then have more cores. We are now here with Intel Broadwell, but we will have Skylake very, very soon, a new microarchitecture, but on a similar manufacturing technology. So with regard to instruction support, then you can really see that we started 10 years ago with the Nehalem on 45 nanometer, and we had SSE 3, then 4, then we got AVX for Sandy Bridge. We are now in the AVX 2 phase, where we have the FMA instruction support in hardware, and we will get AVX 512 very, very soon, which is another 2x potential performance improvement compared to the current product. But then what about software? Here you see a breakdown of the most common HPC workloads. So from CFD to computational structure mechanics, weather, oil and gas, chemistry, molecular dynamics, biology, and also what I call ab initio molecular mechanics. What you then can see is that for the CFD and the CSM, you have very little support for those special instructions because those are ISV codes. they are very worried about the accuracy of their kernels, and they are very reluctant to make any changes to their algorithms because it might influence the accuracy of the result. For oil and gas, it's a bit mixed. Seismic is very integer-oriented, does not scale very, very well in parallel and not really applicable. Reservoir is different. There you can probably factorize very, very well. Chemistry, it depends. The molecular methods generally are not very well suited for factorization because the trip counts of the loops are too small. For molecular dynamics, very, very good. They even have special kernels in assembly. Biology, not really, because integer only again. And in molecular mechanics, using quantum methods, it's very, very big yes. So you can see that it is very, very mixed. So the bottom line is, the ISV support is poor. It's less of an issue for the in-house developed codes or the academic codes, but you have to program it yourself, and it's not easy. Then what about the system performance with regard to bandwidth? You can see, and this is where I plotted all the 0.90 versions of the most popular CPUs. So I started with the Westmere 5690, then the Sandy Ridge, Ivy Ridge, Haswell, and Broadwell. And what you can see is that the clock speed is slowly going down, but the number of cores is going up. The same for the QPI, or the between CPU bandwidth, was going up with the Sandy Ridge because of the extra QPI link, going down, and the same for the memory bandwidth, going down. Luckily, with the upcoming Skylake, where I choose a more or less similar version to the current high-end Broadwell, you can see that it is getting better. So we are getting more cores, so that's a good thing. The clock is going down, unfortunately, but the memory bandwidth and the QPI bandwidth is going up. So hopefully we will get a change compared to the trend. If you add the latency to this, and this is a slide that I stole from John McAlpin, which he presented at Supercomputing, you can see that if we compare the number of flops with the network latency, then we are suffering with 30x per decade. The flops versus memory latency is even worse. It's 100x. If you then compare the bandwidth, well, we are still suffering, but it is less than the latency. So you can say, this is our big problem. How do we get the information to the CPUs? Because we know, with all the big data things going on, the data is becoming sparser and sparser, right? So you have more zeros in your matrix, and therefore it is hard to use SIMD instructions or vector instructions. It's hard to use caches if you don't have much information locally and it's scattered across the system. So therefore you are memory bandwidth, but certainly also latency dependent. So you can say, well, I've known this for years in CFD, but I've now seen it popping up in multiple places. I visited a customer in Ireland who was looking at cattle breeding patterns, and they also have a bandwidth problem. So it is occurring everywhere and everywhere. So then you can say, what does Intel do with regard to these problems? So if we say that our baseline, so the Westmere 5690 was fine, then you can say for bandwidth, well, with the Sandy Ridge, good, we got an extra memory channel, we got more cores, we had new instructions, so we were apparently going in the right direction. And then I am not going to read them all loud, but you can see that Intel is adding more tuning knobs every time with the new processor. With regard to the Snoop mode, we got an extra one with Ivy Bridge, we now have 4 with Broadwell, and with Skylake, you will get also different cluster on die Snoop modes, so even more. Then for the memory bandwidth, larger caches, sometimes extra load store instructions, but again, on the Skylake, it does look quite well. And with regard to the frequency, slowly going down, but we are getting new instructions. So bottom line, more tuning knobs and new instructions. So therefore, you can say that we have to work hard as software programmers. So how do you optimize your software if you don't have the source code? Well, there are various tuning knobs. And if we start with the easy part, which is the hardware, then we can change the BIOS. We can set different P states, for example. We can set different Snoop modes. We can turn off NUMA or use a different memory profile. If we tune the operating system, then we can tune the I/O layer. We can set a process affinity or do something with the memory allocation. Then if you move up to the chain, then if we use MPI, we can tune the MPI layer by making smart decisions about what kind of InfiniBand protocol to use, for example. Do you want to use eager messaging or rendezvous? Or do we want to use a different collective algorithm? Also possible. If you are compute bound, then you can make use of an sophisticated library like the Intel Math Kernel library, for example, or other libraries which will give you better performance. But if you want to really get good performance, then you should make your hands dirty. So you can then change the source code by inserting compiler hints, make real changes, or adding parallelism. The first thing to do on the operating system level is to use affinity. And this is a tool that I've written called Dell Affinity, where the program automatically figures out the architecture of the system. So how many CPUs do I have? How many memory domains? How is it scattered across the system? The core enumeration differs from system to system. What kind of MPI library am I using? It does it all do it by itself and comes up with the optimal placement. And this is an example here where I have a hybrid MPI OpenMP program. You can see that by just using this, you can get a nice 20% almost speed up. Sometimes it can even be more. You can think, well, MPI might be smart because most MPI libraries tend to have process spinning support, but again, sometimes if you use it, you are more intelligent about the architecture, then you can get even better performance. Obviously, it is better to dig one level deeper if you are using MPI. And this is similar to the IPM tool that Pak was presenting in his talk. What the Dell toolbox does is that it profiles the MPI, and then it comes up with 2 comma-separated files that you can load into Excel. And by doing that, you can then create area graphs like this, where you have the walk log time here on the vertical axis and the core number on the horizontal axis. And by doing this, it very clearly shows you what the load imbalance is on your system. So you can see here the blue area that some cores have more work to do than others. And then with the breakdown, you can see how much time is being spent in various MPI routines. It's very, very useful. You can immediately see where you should concentrate on. Then you can also generate graphs like this that tell you something about the amount of messages that are being sent and the size of the messages. So you can then see, well, should I perhaps change my MPI eager or rendezvous crossover points, or should I do something else? Should I perhaps try to combine various MPI calls into one call? And if you do that, and this is something that I did for a Formula 1 team using star CCM Plus, so an ISV application where I didn't have the source code of, then by changing the MPI parameters, you can get a very, very nice 12.6% speed up without changing the source code, just applying some different parameters. Very low-hanging fruit. And the same for example, Altair Hyperworks, where we started with a baseline here, and by tuning 2 knobs, you can get it down by, well, 14%. So very, very useful, and you are getting more performance out of your system. Obviously, the best thing to do is to make changes to the program, and I will conclude my talk by giving you one case study, something that I did for an oil company in the Middle East, and what they are doing with regard to seismic data processing is that they are sending acoustic waves into the surface of the Earth, and they are looking at the scattered and the echo that then comes back. And then you can say something about what is underneath the surface, right? Because different kind of things have a different absorption spectrum. So it really tells you something about what's being hidden under the ground. If you want to map that into a mathematical model, what you then will generally do is that by recreating that spectrum, you are doing a fast Fourier transformation, where you transform from time domain to space domain, or vice versa. And as you probably know, fast Fourier transformations are very memory intensive and very compute intensive as well. So what you then generally do, if you look at a program and you do not know it up front, is that you use some kind of profiler. So what I used here was the Intel Factorization Advisor. It is part of the Intel Parallel Studio Cluster Studio Toolkit, and it tells you something about how much factorization opportunities are inside your program, and it does give you hints about what you should change or not. If we then looked at the program, and this was on a single node, it was an OpenMP threaded program. It's a bit hard to read, I'm afraid, but it said that out of our total CPU time, we had 17 factorized loops, accounting for 23% of the total world clock time, and we had 76% in scalar code, so non-factorized code. So generally, not good performance, and we should factorize definitely some of those scalar loops to get better performance. So, where is it? My laptop's being a bit slow. So when I looked at the source code, I saw things like this, and what they were doing was here some kind of addition with the real and the imaginary parts of an array, and using all kinds of temporary variables. So I simplified that and did do aligned allocation. If you then do that, you look at the output of the compiler, then you can see that we are getting aligned access all of a sudden, and we are having less factorization overhead because of the data alignment. Although this was factorized, this one is factorized even better, and you can see we are having masked loads, which is a good thing, because then we are gaining performance, and you can see that the speed up, because of our changes, is 50% faster compared to the original one. Another problem were the type conversions. So they were doing assignment of variables here to another variable, which is expensive. And you can see, if you look at the compiler output, that you get complaints, because it says, I am doing 12 type converts, and it also does give you that information, obviously. One trick how to get rid of those type conversion is by using a union, where you have a single variable that can have two types in it. It can have an int, or it can have a float type, for example, in my case. And you can, by using that union, you can very, very quickly switch from one part to another. So by doing that, and making those changes and some other fixes, all of a sudden, I'm not having 12 type converts anymore, but only 3. So another way of speeding up the code, you can say. Next thing I did was to look at the memory allocation, because what they did was the following. They have all kinds of frequency windows, so all those acoustic spectra, and each window was being executed on one core. So you think, good stuff, because they are running in parallel. All windows are independent of each other, so therefore I should, with regard to AMDAL, I should have a very embarrassingly parallel speed up. Unfortunately, the memory allocation, so the memory that is needed for those windows, was not allocated in a parallel region, so only in a sequential way. And then what happens, and I do have a picture of that, if the memory allocation is being done by this blue CPU, then what happens is that all the memory ends up on the memory domain where that CPU is, right? And all the windows from the others, or the memory that is needed, is also on this memory domain, which means that they have to work on remote memory, and therefore it suffers. What you then do, obviously, is by doing that same memory allocation, or that actually the touch of the memory, so not the allocation, but you do it in a parallel region, which means that all of a sudden it becomes owned by the thread in question, and then remains also in the memory, giving much better performance. If you then look what actually came out of it, you can see that we started with 23% scalar and 76%, 23% vectorized and 76% scalar. We now have it reversed. So now we have 76% vectorized and 23% scalar. Just by making changes to that code, helping the compiler, all of a sudden it finds opportunities to vectorize better. You then look at the final results, where I started with this baseline. Then I had an optimized version, giving around 25% better performance, or 28% in case of the Haswell, so even better. When I used newer compilers, so not the compilers that the customer was using, even better, right? Because I was using old compilers, and those were released when there was no Haswell hardware present, right? So obviously worse performance than if you use a later one. And then interestingly, if I turned on the FMA instruction specifically, so used AVX2, even better. The only thing is, because of the increased accuracy of the FMA instruction, because you don't do intermediate rounding, you get slightly different results. So if you use the FMA, you should be aware of what you're doing. So very clearly, if you make your hands dirty, you can get, this was 3 days, you can get a very nice performance improvement. So that concludes my talk. Any questions? Yes?
Yeah, so you said that the latency was a big problem.
Yeah.
So what is being done to address this?
What is being done is, in order to overcome that latency, we cannot do much with regard to the memory DIMMs, because that frequency has remained stable, right? So that is not increasing. However, we are getting more and more prefetch instructions in the CPU. So in the night's landing, for example, you have all kinds of software prefetch instructions. And the upcoming Skylake will also have software prefetch instructions that you can use with AVX512. But then again, like I said earlier, it is you as the developer who has to insert those instructions. So no free lunch, unfortunately. Okay, thank you.